Hello everyone. So we already know that these neural networks can achieve significant results with the tasks such as image recognition, image classification, object detection, machine translation, protein folding, and various other tasks with the help of inductive biases such as convolution or sequence attention, really super large data set, and the specialized hardware. The magic behind these amazing eye-popping results are these supermassive models. And these supermassive models are supermassive because of the super large data set is used to train them, which make these models to have billions and billions of parameters. Very soon we will be talking about trillions of parameters. So we already know that these large models are necessary to achieve the strong generalization and the result robustness. So the training with these models with a super large data set is the need of the time, but underneath all these super massive data set based model training lurk a very critical problem. And the problem is the significant use of resources or the requirements to train these supermassive models, which includes specialized hardware that adds up, logistics, cost, power requirement, and top of the above, the feasibility to move the model outside the lab in a real-world environment. So everyone wants to train these models with super large data set while limiting their resource requirement. And that is everybody's requirement, or this is everybody's need. So let's make the problem clear now. So the problem is that models can be trained with supermassive data sets, but the need of these massive, supermassive resource requirement is the biggest problem underneath. And everybody wants to scale up these models so these models can have supermassive size of parameters without scaling up the additional computational resources. And the approach to solve this problem is to use conditional computations. So in conditional computations, rather than activating the whole network for every single input, it's better to only activate different parts of the model which are activated only for different inputs. Since 1991, there has been a lot of work, theoretical as well as some practical, has been done to develop mixture of experts in a variety of ways. However, the most important thing to note here is that the mixture of expert is used as a general purpose neural network component in this mixture of experts research paper and the implementation by Google. So before we go deeper, let's take a look at the sparse and the dense models. So with the dense models, every part of a model processing every input. It means whole model is running for every input. Comparative to dense, the sparse models, they apply conditional computations to learn how to route individual inputs to the different experts in a potentially huge network. It means that if we apply more and more sparse models, we can achieve the high model capacity without compromising the computational resources, right? And that is a potential solution. So while we are on this topic, let's take a look at the pathway models. The term is not very new, but it is very important to understand the whole idea behind mixtures of experts. So the pathway summarizes the research vision of building a one single very large model that intelligently handles thousands of tasks and numerous data modalities. The sparse unimodels for the language are already available, such as Switch, Task MoE, GLAM. If we look into these pathway models for the computer visions, we can find that vision MoE is also available. And very recently, you must have heard about LIMOE. In this LIMOE, the sparse model is handling both text and images, means it adds up the multimodality, and that's the reason it is very important. So now let's combine all of this thing together. It means if we combine both sparse and dense model together, and within the sparse model architecture add these mixtures of experts, we can achieve very high model capacity without compromising the additional computational requirements. Now let's take a quick look into what is MoE, or the mixture of experts, and what is its internal architecture, how it works, and how it processes the data to achieve significant model capacity upgrade without compromising or without any additional need of computational resources. So the mixture of experts, or the MoE, uses multiple expert networks to divide a problem into homogeneous regions. It means a problem is divided into multiple small subset of problems, and these small experts are the learners, and they work individually on a subset of the problem. So the architecture wise, you can see that a MoE is having two main components. One is going to be your gating network, or the router here, and the second, a large collection of experts. This MoE transformer block, or we could say the MoE layer, can be sandwiched between the two dense transformer blocks. One thing you must understand is that MoE transformer block is designed with a sparse model. It means the input is going to be processed by the different experts as the information processed by the router. However, the information arriving to the MoE layer is going through with a dense transformer block. It means the input data is going to be processed by this dense transformer block, which is going to process all the information for full input. That input is going to be given to the router, which takes all the information here and then route depending on which expert a particular router chooses, or the number of experts it chooses. And finally, the output will be sent to the output layer. However, if it is needed, then another MoE transformer block can also be added. It means if we try to look the whole pipeline, we can say that the MoE layer can be sandwiched between the dense transformer block depending on what the need is. So we must understand that mixture of expert is very different from the ensemble method of solving problem. In ensemble method, we have a data set where the problem arises or the problem stays on, and we have a group of algorithms to process this data, and we take the exact data set and create multiple copies of this data so that each individual algorithm can work on full data set and can solve the problem by its own way. Finally, the data is being processed by the algorithm, and the predictions or the results are generated individually by the each algorithm depending on their own processing. These individual results are blended together with another set of algorithm where a final output is generated, and this result is actually generated based on the combined result of previous algorithms. That's why this method can also be considered as a blended method. The ensembles or the blending algorithms are available in mostly all available machine learning platform or the libraries available. One example can be seen with the Data Robot AI platform. Here you could see that this MED blender or the median blender is actually a blending process where the results from two different models has been processed together, and a final the median blender is created. So we must not confuse ourselves to MoE or the mixtures of experts to the ensemble or the blending. Now we are going to go deeper into the architecture of two main components of mixture of experts. The MoE consists of a number of experts. Each expert is a simple feed-forward neural network and a trainable gating network which selects a sparse combination of experts to process each input. Mixture of experts can be used to solve problems related with language modeling, machine translations, various vision related problems, and now combining with the multi-modality. The all parts of the networks are trained jointly by the back propagation. So what we are seeing here is the MoE layer, and the output of the MoE layer is passed through a sigmoid function. So the final output of the MoE layer is passed through sigmoid function before dropout. Now going deeper into each expert, which is a feed-forward network, we can see that there are various hidden layers and the output layers. In one example, we can say that each feed-forward network has one ReLU activated hidden layer of the size 1024 and an output layer of size 512. And when these layers are fully connected, we can say that each feed-forward network expert contains about 1 million parameters, and the math is already given in front of you. Adding more layers to each feed-forward network or the expert can enhance the parameters at each expert level. Each MoE layer can have thousands of experts in it, and these experts can build either the ordinary MoE layer or the hierarchical MoE layers. So putting more focus at the feed-forward network or the experts layer, we can say that if we have 4 experts, we can call it MoE 4 or MoE 32 for a 32 expert network, or MoE 256 for a 256 experts network. However, with the hierarchical MoE layers having 256 or 1024 or the 4096 experts, these MoE layers can be called MoE 256H or MoE 1024H or the MoE 4096H. So the various combinations can be created in order to fulfill the requirement of model capacity without compromising or without need of additional computational requirement. Now let's take a look that whether we are using text MoE or the vision MoE. It means processing either text or the images through a mixture of experts how data is processed. Let's start with text first. It means you have a large collection of text that is available for you. The very first step for you is to tokenize your text. At this point, your text has been converted into the vector and the tokens, and these tokens are processed directly through a dense transformer block, which could be an optional component here. So either through a direct connection, these tokens can be made available to this trainable gating network or the router, or coming through dense transformer block, the tokens are going to arrive at router, where these tokens has to be processed in real time and sent to individual experts or the feed forward network. We must remember that the training gateway as well as these feed forward network experts, they has already been trained using the backpropagation to understand which expert should be chosen by the router. So it means the trainable gateway network is acting definitely as a router here to send those tokens to the individual experts as per its own discretion. Each expert is processing its own share of tokens, and finally the results are aggregated and sent to the sigmoid function before being passed to the output layer. Few things to note here is that at every MoE layer level, all the results from all the experts are aggregated together and then they are passed to the output layer through a sigmoid function. Now we can learn the same processing for a vision MoE. It means how the images are processed. First, we have a group of images. These images are split into a group of patches. You must understand the patches here are a small subsection of the image, maybe a 16 by 16 image block. To learn more about this process, I would request you to please take a look at the VIT Vision Transformer, and you will learn the logics behind splitting image at the patch level. Once the images are tokenized, they are ready to be sent to the Vision MoE. Whether the network has a dense transformer block or not, finally these images arrived at the router, where router has already been trained for finding the most suitable expert depending on input image requirements. Router works and starts sending the group of images to individual experts, and finally the aggregated results of all these images has been sent to the output layer through a sigmoid function. But here is a catch. If you remember, there are lots of images, and for a sparse model and the transformer architecture, all the image or all the input data has been processed together at the same time. It means the aggregation is going to wait for each MoE layer for all the input data to be processed completely. It means the MoE layer will wait for all the incoming input data to be processed completely before it is going to combine the output and send it to output layer. More data is available and the router process all the incoming data and send to individual experts, and finally the experts are grouping all the result data, and the final aggregated result data is sent to output layer through the sigmoid function. Very recently, just few days back, Google announced LIMOE, where using mixture of experts to process both text and the images together. It means the multiple modalities capable mixture of experts. Here you can see the LIMOE architecture is processing both text and the images as inputs, and many experts and the routers are working together to decide which particular expert is going to process what input data or the input tokens, and the final output layer computes a single vector representation of the results, either for an image or for a text. The detailed research paper related with sparsely-gated mixtures of expert, or the SGMOU, is one of the best resource for you to review. If your interest is to use the code, then I would suggest you to look into the mixture of experts implementation here, and this implementation is totally based on this SGMOU research paper by Google, and all of this information I have put together in this GitHub repo, DeepWorks folder MoE. So the content related with this video I have covered is all available, and few important resources, they are all available for you to review as your time becomes available.